Hey guys, this is Alan with Bothell STEM Coach, and today we are going to do a mini lesson on rotational motion for AP Physics 1. Now, the reason I would normally do videos on just problem solving, and I will do more problem solving videos, but I do want to start with a primer on the basics of rotational motion. When I have students on AP Physics 1 come to me, the biggest thing that I note that they don't quite understand is rotational motion. So I want to make sure that we're all kind of starting on the same page about what torque is, what the forces are, how do you calculate all these things, and what's important before we just jump right into problems. Okay. One of the reasons that this may be more confusing is this is a relatively new topic for the algebra-based AP Physics courses. Back in AP Physics B, you didn't need to know any of the rotational mechanics. You didn't need to know it for AP Physics C, so those students are still kind of versed in this topic. But this is a new topic they added when they revamped AP Physics B into AP Physics 1 and 2 back in 2015. So it's relatively new, and that's why the topic doesn't get a lot of treatment, I think, under normal curriculum. So let's talk about what we mean by rotational motion. So everything we've learned so far is still true. You know, we've been doing free body diagrams. I have an object, I apply a force on it, say upward, and it will accelerate in that direction in a linear motion. Okay? But things don't always move in a straight line when they push them. Not their path, but they may turn along the way, right? So for example, if I pushed on this end of this sort of block, it would slide along with an acceleration. Okay, it would move along translation. That part is still true. So say, but it would also turn while it was doing it. It would tend to like turn this way. Hopefully that's the right. Maybe this way from your perspective. Kind of depends. I don't know. My camera is kind of maybe a little bit backwards. But it will turn along that that direction as you're pushing it. So if I push this way, not only does it move upward linearly in a translational kind of movement, but it will also rotate too. Okay, and so as part of rotational motion, we want to understand that. How is it rotating? What's the speed that it rotates at, and everything like that. Okay, so we introduce a new type of quantity called the torque. Now, there's actually a few formulas that relate torque. I'm going to give you the raw formula in vector form. But in AP Physics 1, you may not understand what this is. So, in general, torque is R cross F. And I only give that to people who are familiar with what a cross product is between two vectors. And if you want to look that up, that's fine. Again, you don't need to know that for AP Physics 1. But what this is there's two things that are a consequence of this. One, torque is definitely a vector. So that means it has both direction and it has magnitude. Okay, just like a force. Two, it's related to two vectors. The force that's being applied and the r, which is the distance that the force is being applied. And as an example, torque is sort of, we'll get to what it means, but torque is what's going to cause a rotational motion. Just like force, like when I apply a force, it causes acceleration, right? When I apply a torque, it causes rotation. Okay? Another way we kind of say this, which I'll get into, is it causes angular acceleration. Okay? So that's the idea. If I apply, sometimes when we use torque, we use the Greek letter tau for torque, because we use T for enough things, so someone decided to use the Greek letter tau, and it looks like this, kind of a T with a little curl at the end. This is the Greek letter tau, and it stands for torque, typically when you study mechanics. Okay, so torque causes a rotation, and so let's talk about this R quantity. To cause a rotation, it matters how far. It matters two things: how strong of a force you apply, and also how far it is from the point of rotation. Okay, you might think of this like a seesaw, kind of, when it seesaws like this. Like, the further I apply the force, if I apply the same force, it's going to rotate more than if I apply closer to the center of the point of rotation. Okay, that's the idea. So it's based on these two quantities. Now, the second question is okay, what does this cross product have to do? Well, the thing about force is, in order to cause a rotation, so like if I apply this force, this is going to cause this thing to rotate like that way, right? Like that's the way it's going to spin. The thing about the force is it will only cause a rotation if it's acting at a distance that's perpendicular to the point of rotation. So for example, if I applied the same force, say this is the point of rotation, but instead of applying the force vertically, I applied the force like this at the end. Okay. This would have the torque here would be 0. Because the force is parallel to this r vector. Okay, so the r vector is a vector that's drawn from the point of rotation to where the force is applied. Okay, let's do another example. Say I have another thing like this, and I apply a force right here. And for simplicity, I'm going to say I apply it like right here on the block. Well, my r vector would look like this. It's a vector from the point of rotation to where the force is being applied, and then the f vector is like this. Now, the r cross f to calculate the torque is I only care about the part of the force that's perpendicular to r. So I have to split this vector f into its horizontal and vertical components. Say this is f sub x, this is f sub y. And the torque would then equal to this distance r times f sub y. Okay? Because I want the portion that's perpendicular to the r vector. Okay? This is a pretty tricky point, so I want to make sure we emphasize this point. The torque is only the portion of the force or r vector that are perpendicular to one another. Okay? So what do we do with this torque? Similarly to how when you do a net force and it causes an acceleration, what you do is you do a net torque, and it causes angular acceleration. So normally I have, for linear motion, I have net force equals mass times acceleration. When I do a net torque, it's equal to something that looks like an A. This is alpha, the Greek letter for A, and it refers to angular acceleration. I is kind of like mass, analogous. We called this rotational inertia. That's how it's referred to in AP Physics 1. Sometimes it's also called moment of inertia. Moment of inertia. That's another term for it. Okay, but they mean the same thing. And I is, you don't have to know how to compute I for an object in AP Physics 1. In principle, it is simply how hard it is to rotate an object. So having more mass can make it hard to rotate, but also like where the mass is positioned can make something hard to rotate. So I know that's really ambiguous, but I is typically just something that's given to you as far as AP Physics 1 is concerned. But in a more complicated, more advanced mechanics class, you would compute I. And actually you had to compute I back in the AP Physics B days, maybe? I don't know. But in a lot of physics classes, in college, you will have to be able to compute what the moment of inertia. But for now, you're not gonna have any problems that ask you to solve for what I is. Just certain of this. Okay, but it's sort of either given to you, kind of like the mass of an object's given to you in a problem. I would be given to you in a problem. It would be a property of the object itself. And so what you would say is the net torque is equal to the rotational inertia times alpha. If I can calculate what the net torque is, and I know what I is, I can calculate what the angular acceleration is. Alpha has units radians per second squared. Okay? And the radians is sort of the change in angle per second squared. Kind of like acceleration is meters per second squared. This is acceleration. Angular acceleration is radians per second squared. Okay, so that's typically how the setup's going to be. It's going to be a lot of net torque, calculating the net torque, and then applying this kind of formula. So in the next videos for rotational inertia, I will go into all of that, setting up those kinds of problems. I also want to emphasize that there are other quantities that you will learn about when you're dealing with rotational inertia that are very analogous to linear motion. So kind of like, I like to make this list of sort of linear motion quantities and relate them to their rotational equivalents. Okay, linear motion. We have position, velocity, acceleration, force. We have the quantity momentum, which we usually use P. We have the quantity energy. Energy is 1/2 mv squared. So these are all quantities that we have in linear motion. Okay, in rotational motion, position is the angle that I'm at. Velocity is angular velocity. Acceleration is angular acceleration. Instead of force, we have torque. And instead of linear momentum, we have angular momentum, which usually used as L. It's given by I omega. And you have an energy here, rotational energy, I omega squared. These quantities, you can kind of see that they're related to these. Like m times v, I replace it with I times omega, because there's sort of a correspondence between these two, if that makes sense. So somehow that's making me easier to help memorize equations or get an understanding of these things. Okay, so similarly to conservation of momentum, there's conservation of angular momentum. Similar to conservation of energy, when it applies, there's an energy used in causing something to rotate too. So something will have rotational energy as well as. So this is kinetic energy due to linear motion. This is kinetic energy due to rotational motion, or rotational energy. Okay. So that was a really quick primer, just trying to go over the very basics of torque. I like to learn by doing problems, so we'll be moving on to doing very specific rotational free response questions, and just practicing, getting used to setting up the free body diagram, setting up the forces, calculating what torque is. Okay? Hope you guys found that helpful. I'll see you guys in the next video. Thanks for watching the video, guys. Please leave a comment, like, or subscribe below to catch up more of the content. And see any links below. I offer free homework help on Twitch and Discord. See you guys in the next video.